Ahead and get started because we have a lot to cover. So welcome to this session, and I have to make a few announcements to start with. Please don't forget that there are some great posters downstairs in the exhibition area. So if you can, please go there during the breaks, especially during the afternoon coffee break. The presenters are going to be there to talk to you if you're there, so please take a look. Don't forget also that there are demonstrations scheduled every break in the demo area. You can check the online pages for the schedule on that. Please, it's really important that you give us your feedback on the session, on anything you want to provide feedback on the conference. This is what helps us make a better conference. So please use the application, the mobile app, or go online for your feedback, or reach out to any one of us from the program committee. Gala dinner, again, is today. Please make sure you are there on time for the buses that are going to leave from the different places. There is a bus also that's leaving from the pier side on this building at 7:15. And there was an announcement sent too on the shuttle buses from hotels and all that. So if there are any questions, please go to registration. I don't know what all the buses are going to be, so don't ask me. But please go to that registration information desk. Tomorrow morning, again, we're starting 30 minutes later with some coffee and tea, so a little bit more time to sleep in case you have a great time tonight and stay up a little bit late. But wonderful sessions happening tomorrow, so please don't skip those. And there's a presidential car museum here in this great place that we are. And it's on the first floor, and you can visit for free. So there's that. So those announcements covered. Welcome to this session titled Big Science. My name is Anna Hunsinger. I am a member of the program committee for this conference, but I'm also the vice president for community engagement at Internet 2 in the United States. So it's a great honor. Very great honor to be here. And my role is very easy today because I just get to chair and be the meantime keeper that's going to try to keep us on schedule here. But big science, so big name for a big session here. And, you know, if you look at how big science gets defined, there's this very generic definition. This is kind of out of Wikipedia about big science being, in a very generic, defined way, all the series of changes in science that have taken place in industrial nations, and after World War II, as scientific progress has increasingly come to rely on very large-scale projects and facilities, usually funded by one or more often several governments, groups of governments, and many nations working together. In the context of this conference and for the work that we do in National Research and Education Networks, I'm taking some liberties here, but I think big science in our context here is really to talk about the science that is possible by the work that we do to support the foundations of the infrastructure that can support that. So not just the network, but above that network, a whole bunch of things that have to take place, and how we need to provide scalable, robust, advanced network platforms. And platform, again, not just the underlying infrastructure, but other things like security too. And what is the role that National Research and Education Networks can play with that? Today we're going to talk about big science in the context of large-scale facilities in the astronomy context, so fascinating area. And we're going to cover things from what's happening with a particular project that's very important to Europe, the Copernicus project. Then we're going to talk about the Square Kilometer Array, another multi-nation project that has multiple entrants working together. And then we're going to go a little bit more to a specific case study within a country in Chile. And again, all of this around the wide context of astronomy. Clearly in astronomy, there's all kinds of things happening too. So with that said, we have a great set of speakers here. My plan for today is that I'm going to introduce the speakers in the order that we have agreed, and then they have 15 minutes to present, and then we have left some time for questions specific to that presentation. If there are more questions to that presentation and we're running short on the time, I will ask that we hold those questions towards the end. My hope is that we have some questions at the end for everybody to bring up. Maybe we find some common themes. So I encourage you to think about those things. Okay, our first presenter is Francesco Nisi. Francesco is a network architect and consultant at the European Space Agency in the EOPGS Infrastructure and Operations Management Division, and he's been there since 2009. Francesco is going to cover, title of his presentation is there, so no need to repeat it. So let's get started.
So, good morning, everybody. So thank you, Anna, for the introduction. So we want to present and share with you our experience in building up a network and security solution for the Copernicus program. So what is Copernicus? Copernicus is a European space program led by the European Union, which has the objective to provide data for environment monitoring, for civil security, for example, images for earthquakes, floods, and so on. The program is composed by a space component, which are the fleet of satellites called Sentinels, equipped with a new generation of instruments, which generate data of several terabytes per day. And all this data, for the first time, are provided thanks to the new data policy, free and open to everybody. It means that each of you can download all these raw data generated by the satellites just few hours before. And all this data have to be distributed to a wide user community, so that it's composed by the general public, plus institutions and scientific users. ESA is responsible for the deployment and operation of the space component, which is composed of the satellites, of course, plus all the infrastructure on Earth to receive, process, and distribute all the data to the user communities. So the main functions of this ground segment are, of course, the circulation network, which transfers the data between the facilities, plus the dissemination network, which is in charge to distribute all this data to all the users, all the user communities. So ESA had to build this infrastructure. So what we've done, we started in 2012 with an open tender, which according to ESA procurement regulations. And after a few months, in early 2013, the contract was awarded to a commercial company. After a few months of the design deployment in September, in 6 months, the first 5 facilities were ready in operation to support the Sentinel's operations. So the big challenges for us were to design and deploy our infrastructure with high speed. It means 10 gig connections. Scalable, because we don't know how much traffic the users will download. And of course, secure, because we have at the same time to ensure security, but to open our network to a broad range of user communities. So, our ground segment. You can see from the slides, our ground segment is distributed across Europe. Most of the centers are in the mainland Europe, plus some of the receiving stations are very far away. For example, Svalbard and Maspalomas, which are thousands of kilometers away from Central Europe. Of course, each center is specialized for each function, but from the network point of view, the most important is the central infrastructure, which is located in Frankfurt, where we will see is hosting most of our network security services. So, our solution, we wanted to have as much as possible a centralized solution in order to make easier the management and the control of all of our services. So in Frankfurt, we have 2 data centers, twin data centers, because we have full redundancy, which are hosting the internet access infrastructure, so the internet breakouts, all auxiliary services such as DNS, NTP, proxy, mail relay, and so on. And more importantly, pick-up point infrastructure. We will see the core service we have put in place to distribute all the data to our user communities. All these sites are connected to our internet service, which is composed by an access network based on Dwdm technology. So each site is connected to the central hub in Frankfurt via 2 10 gig lines, most of the sites. And we have configured our IPM MPLS network to use both links in the same time. So we generally use one link for data circulation between the facility, the other one for the dissemination to the user communities. And in theory, we can have 2 times 10 gig as peak value for transfer rate from one facility to another. And currently, they are already heavy loaded. So how all this infrastructure is connected to the rest of the world? How we send traffic out of Copernicus infrastructure? The first exit point is the main internet access. It's a redundant infrastructure with 2 10 gig redundant links. They are connected to, of course, an autonomous system managed by a commercial provider, which is the same provider, of course, that is managing all the services. Through this connection, we are able to reach all the general public, which is one of the user communities, and also the scientific communities. Particular attention for Géant, because currently with this setup, also the academic user connected to sitting on Géant network, in order to reach our Copernicus data, have to cross the public, the commercial internet at the moment. So since we know that the traffic is constantly increasing from Copernicus to Géant academic communities, we are planning a direct interconnection between Géant and Copernicus network. So all these class of users will have a 10 gig dedicated bandwidth to retrieve all the Sentinels data. The second exit point for the Copernicus data is the pickup point service. This is infrastructure that we have decided to implement in Frankfurt, so in the Central Europe, near to the backbone. So in this way, all the users that have to get to the Copernicus data can benefit of a lower round-trip delay and should have a higher throughput for the download. This infrastructure provides a virtualized systems to build our application for dissemination, plus a scalable storage to host the last 12 months of all the Sentinels data. Currently, we have 1 petabyte, will be 3 petabytes in a short time, and will increase over the time as the new Sentinel satellites will generate new data, new traffic. Also, for this connection, academic users will be able to get the data through the dedicated connection. The main challenge was to enforce the security with this high speed. It means we have 10 gig data flows, and we need to check all this traffic at this speed. We have built a defense perimeters based on the state-of-the-art technology for the security, which has multiple layers, starting from denial of service appliances on the internet breakouts, going to central and local firewall equipped with intrusion detection systems, and arriving, very more important, up to end systems, which have to follow an hardening process in order to eliminate all the possible vulnerabilities. All this infrastructure is ruled by our Earth observation security policy. So we have configured all the equipment just to open what is needed. And we have strict procedures to make sure that each device is always up to date and fine-tuned to avoid also the more recent attacks. My colleague Barbara in the next speech will provide you more information about our approach on the security for Copernicus. Service model. As I said before, all these services have been awarded to a single contractor, single company. So we have a single point of contact for all the services I've listed before, so connectivity, security, auxiliary services, or whatever. And all these services, of course, are controlled through a service level agreement with precise KPIs and, of course, with a penalty scheme associated for each of them. This, of course, the objective of this choice is to simplify, from the ESA point of view, the management of this complex infrastructure. So in the end, we have a single point of contact to manage all these services. Particular attention has been given to verification and validation of the whole infrastructure. We spent a lot of time to go all these testing areas, so functional testing, performance, redundancy, and security. I want to provide here just some findings related to the performance testing, because throughput is really a key parameter for this high-speed network and for expectations from the user communities to retrieve the data. As most of you already know, the parameters that can have some impact on the throughput are round-trip delay and packet loss in the lines. So we face the same issues that already know. What we can say that on our infrastructure, the private part, we have no packet loss ratio. We have configured the network to be jumbo frame ready end-to-end. So, and systems are able to get maximum performance on our network. The weak point here is the server, the endpoint, because we have played a lot of testing, playing with the main parameters. For example, the buffer size for the TCP stack, just to improve the TCP windowing, and also some congestion avoidance algorithm. We have collected a lot of statistics. We have tried to summarize here, but what we have found that unfortunately does not exist a magic formula. We cannot say this is the best configuration for all the systems in the end, because some parameters are more effective in some scenarios and other parameters in other scenarios. So in essence, we have prepared a sort of guidelines for our internal project, which are responsible for the server configurations. In this way, each project can test, verify, can get the higher performance possible on our infrastructure. Similar issues have been faced, of course, for internet access, for the user community sitting on the internet that needs to access our network. Here it's more difficult because the internet is not under our control. But we have had a test campaign with some users. We played a lot, and we have been able to find that for user communities sitting in Europe, if we fine-tune the servers, we can reach high throughputs also for these users. For others that maybe are overseas, very far away, is more difficult because the internet path is longer and the performance cannot be ensured. And of course, in some cases, the weak point has been, again, or the end system on the users or the bandwidth limitation for the local internet access for the user. So in the end, we are in operation with Copernicus networks since December 2013. So far, we can state that the performance and the design has provided a good result. We are providing successfully connectivity for all the Sentinel projects and also for the community that are downloading the Sentinel-1 Copernicus data since last year. We are sending hundreds of terabytes of data per month at the moment, and in a few months we will have new satellites in orbit, and this data will increase. So, what's next? For sure, the next challenge we have is to further increase our dissemination capabilities, because it's hardly predictable how amount of data that will be retrieved. So we are preparing to add additional, let's say, power to our dissemination network. As next step, in a few months, we will have also this connectivity for Giant, which is for us a specific user community. And we are also willing to investigate, implement some performance monitoring solution between our network where the sensitive data is and all the possible user communities, not only on our infrastructure, but around the world on the internet. So if you are interested, some result of these Copernicus programs or what scientists are doing with our data will be presented last year in the ESA event. Okay, so thank you for listening. One more thing.
I guess I will repeat this. We have time for some questions. Are there any questions?
Have your investigations into the throughput tests from locations that are distant from the data center revealed any hints as to what you would need to optimize and fine-tune to get to 10 gigabit throughputs?
So I'm not sure I get your question. If you could kindly repeat.
So you showed slides showing your testing from various universities in terms of throughput.
Yeah.
Do you have any indication what fine-tuning is necessary to achieve higher throughputs?
Well, thank you for your question, but it's not so easy to answer because we have found different parameter settings depending on the type of traffic. For example, one of the major findings has been, of course, that sending files with big size can have higher throughput. And in this case, some congestion algorithm is better than others. And for sure, one of the parameters that have to be fine-tuned are the buffer on the system, for the receiving buffer and sending buffer. And make sure that the TCP window scaling factor is properly working on the machine. Because also during the months of operations, we have been investigating on several performance issues. And in all the cases, we found out that the issue was on the system because of a bad configuration for the TCP stack. Or sometimes the disk access very low that was compromising the performance. Just an additional note, we had testing with a user in UK where we performed an FTP session from memory to memory without reading or writing the data on the disk. So only pure network. And with 45 milliseconds of relative delay, we reached almost 900 megabits per second. So it means that the network itself is capable to support this very high-speed network, but the end systems and how they are configured and how the application are using the network are the weak point.
Thank you.
Yeah.
Good day. I've got a question around your firewall testing. Did you, was that a bottleneck at any point? And specifically, what is the maximum single flow that you could get through your firewall configuration?
Yeah, the tests have been done on a single TCP flow, of course, but the application can send data in parallel. But what we want to make sure that the single flow is at the best configuration possible, and then to leave the application level to start multiple download in parallel, if possible. Considering our setup, we have the satellite orbiting. He passes over the receiving station, And before the satellite passes again on the station, we need to download and move the data as soon as possible. So our traffic pattern is no traffic, burst up to line speed, and then empty and waiting for the new satellite pass. So it's important to us to move out the data as soon as possible from the receiving point.
I just like to complement the sentence of Francesco. We have the result of the test plan and the technical note written by the team of Copernicus to improve the performance of the end user. So if you drop an email to Francesco, you can get fine-tuning for your application.
For your note, Mr. Gioacchino Buscemi is, from ESA is leading the Network Security Health Preservation Office, of course. So, thank you, everybody.
Thank you very much. Thank you, Francesco. Our next presenter is Barbara Angelucci. She is also an secure and she's been working a lot also, as I understand, with that agency security framework. So she's going to deep dive a little bit more, of course, in the area of security around a little bit what Francesco mentioned. So Barbara?
Thanks, Anna, for your introduction. Good morning, everybody. I will be giving you a different perspective on the Copernicus program that we've been dealing with inside the European Space Agency, the security perspective. I will describe very briefly the context where we are in, and then I will describe you the approach that we have adopted in order to address the security in this huge program. And we basically identified two different approaches, two different perspectives to address security. One is the security framework, and the other one is the project lifecycle management. I'm going into them a bit more. Okay, this slide has been already presented by my colleague Francesco. This is the Copernicus program, a European system for the establishment of European capacity to access key environmental data on a routine basis. We have basically three components. The service component is the one that already mentioned Francesco, where the program is aimed to provide information about land monitoring, marine environment monitoring, atmosphere monitoring, emergency management, security, and climate change. In this context, the space component is the part of the infrastructures where information are provided by the satellites. We have the Sentinel satellites that are being developed and operated by the European Space Agency, and all the information provided by the satellite are acquired by the ground segment. The ground segment is a set of facilities that are acquiring the information through receiving stations. They are processing, archiving, and distributing the information to the end users. But the Copernicus program is not only the ESA part. There are also contributing missions from other space agencies that are providing information to contribute to the services, and other collaborative centers. Altogether, they are coordinated in order to feed the service component to provide information to the end users. The scope of the activity that we have done in the agency at the ground segment department is this one. Here we have a collection of ground segments that have to work collectively together in a seamless manner to provide a seamless service to the end users. So what approach did we use to do this? There are two main drivers. The first one are the security objectives of the Copernicus program. The Copernicus program is to ensure access to information in case of emergency and critical situation to manage disasters, man-made or natural disasters. The information have to be delivered in accurate, reliable, and sustainable manner. Whatever the amount of data that we need to deliver, they have to be there. Information has to be there when needed and as needed. The other driver is the European Commission data policy. The European Commission states that Copernicus has to grant full, free, and open access to the data provided. Of course, there are specific limitations that are to be taken into account, like licensing conditions, security interests of the member states, reliable access, but most of all, our role is to take care for this, risk of the disruption of the Copernicus infrastructure. We need to preserve this ground segment. The environment is pretty complex. This is the challenge that we have to face with is due to the fact that we have a lot of different missions that have to provide different informations, a lot of industries that are building the satellites and the ground segments, several contracts. So, and all of them have to work together in order to provide a seamless service and a seamless infrastructure. But this is also a dynamic infrastructure because new sentinels, new missions are being delivered. Service requirements are changes, new business needs are coming out, also from the European Commissions, and we need to be able to provide real-time data anyway. So we need to find a way to grant security from an end-to-end perspective, taking into account all the different actors and all the different situations that we can get in. So what we have decided so to approach the security we need to find a methodology, a method that allows us to look at security from two different perspectives, the technical one and the organizational one, the management one. So from the technical perspective, we had to define the technical measures that were necessary to, first of all, be compliant with the data policy and the security objectives of the Copernicus program. Then they need to be able to face the risks that we have identified with the initial risk assessment exercise, like this. I'm sorry. Okay, I have to skip back. Okay. And then we need to be able to serve the security of the objectives of the Copernicus program in line with the security standards and security best practice. From the management perspective, the technical measures have to be designed, implemented, operated, and injected into and every project that is involved in the Copernicus program, into every element. So we need to inject it inside the project management life cycle. Now, let's look at the first. Let's look better into the first perspective, the security framework. The security framework is basically a set of requirements and a set of operations and organization measures. Requirements have been defined in order to address several domains identified based on the risk analysis. And the operations are necessary because every security measure has to be operated and maintained and managed over time. So here we have a security operation and a security organization. We got both a bit in depth into these security domains to see what they are about, what they mean in our environment. System and application security. These domains address the security of the issues that may derive at operating system and application level. So here we take care about operating system hardening, security patching, secure coding practices. We have a lot of custom developed applications, a strategy to deal with systems of obsolescence, the verification of the inputs to data, the inputs to systems coming from other systems or from humans, because they need to be validated in terms of syntactic and semantics in order to be sure that they're not injecting any malicious malware inside the system. Just to give you an idea of the complexity and the numbers, we have to inject these requirements in more than 1,200 servers. We have been dealing with more than 100 applications, and we've been good at keeping the OS types numbers to 5, just to 5. At network level, we have defined a network reference architecture that defines the different security levels, different security zones, and also the screening policy and the traffic policy and the baseline of all the traffic that is allowed to go between the different security zones, implemented by the firewall and other security measures. In this way, if every system and every solution in our network is compliant with this reference architecture, we have systems with the same security needs grouped in the same security zones. We are able to grant their security to manage their security needs. over the time. As Francesco has shown in the wide area network, we have implemented the network reference architecture through the firewall, a central firewall system that screens all the access from to the internet, and a set of local firewalls and intrusion detection and prevention systems that implements the security zone and screen all the traffic inside the local centers and between centers, all the circulation traffic. Here we have connected 11 centers, and we have deployed more than 40 security devices over the wide area network. Access control, I think this is the heart of this work, the most trivial part, the most difficult part. We have a huge amount of data to be distributed. We have heterogeneous users community, so we need to implement a granular access control policy in order to ensure that intended users are able to access only whether authorized to access. So how we did it? We defined a set of data classes. Here we are talking only about unclassified data. Classified data do not enter into the scene of the Copernicus program. These classes have been defined based on their information assurance properties like confidentiality, integrity, availability, authenticity, and non-repudiation. Afterwards, we have built a catalog of all the information involved in all the missions that belong to this program, from the satellite data up to the documentation that belongs to each project. They have been mapped to the classes according to their security needs, and so we have been able to define the security measures that was necessary to implement to access each of these data. This means that I can say to any project, where can I store some kind of information, the DMZ or the internal LAN, what kind of authentication measure I need to implement, what kind of authorization I need to implement, if I need some kind of encryption, so what kind of protocols I can use to access this information. On the other side, we have users. How can we grant that user can access those data? We have defined categories of users, from the administrators, operators, to the end users that are retrieving the data from our DMZ. And we have defined the access right matrix that, in order to be able to define who can access what, following the established security measures. From the security operations and management, we have defined the procedures, but beyond the procedures, we have set up an organization. The most important is the Security Control Board that is in charge to maintain the security level of the Copernicus program, of these systems, of this ground segment, stable over time, to manage any changes, any new requirements, and ensure that we don't exceed the accepted risk level. Project lifecycle management. Once we have defined the security measures, we need to inject them properly into each and every project, into each phase. We need to ensure that they're properly designed, deployed, implemented, verified, and at the end, decommissioned at the end of the cycle. And we did this for all the missions, for the Copernicus one, for all the components that belongs to the different missions. And then we are sure that where the integration is completed end-to-end, from the Copernicus one to the LAN at each centers to the deployment of each PDS, we still keep the same security level. Everything works smoothly from end to end. Probably you already heard this several times, security is as strong as the weakest link. So, to conclude, let's make a summary of some facts and numbers. The Copernicus one connects 11 different centers. We have two data centers that provide central security services. Up to now, we have deployed the 3 ground segments, the 3 sentinels, that are made of about more than 100,000 servers. Over about 75 of them are exposed over the internet. We had to manage more than 100 custom applications. Up to now, Sentinel-1A, the only satellite that is in orbit in this moment, is circulated alone more than 260 terabytes of data per month. More than 40 different data classes, hundreds of users, and this is all together. And with this approach, we have been able to keep under control the security of the Copernicus up to now. So basically, we can say a 4D approach. From a vertical perspective, we have injected the security into each and every program. Then we have ensured that end-to-end, everything is integrated correctly, and then we manage the security over time through the organization. We hope that we'll define a consistent manner, a methodology to take the security under control in our Copernicus environment. If we are lucky, we will see good results in the next Living Planet Symposium organized by ESA. And with this, I have finished my presentation.
Time for questions.
Thank you very much for that. You have a large and complex system. Any system, after it's launched, it tends to drift a little bit from its ideal state. I wonder if you can say anything about your change management process. I'm particularly curious to know whether you use any sort of infrastructure automation to help maintain state.
Yeah, I have to skip this was one of the topics in my slide, but I have to skip it quickly. Oh, I'm sorry. I have to go quickly for that, but we have set up a set of coordinated end-to-end procedures in order to manage, to keep under control changes and configurations and requirements changes. Every entity has its own change management, but we have defined an overall coordinated procedures that is everybody has to follow in order to ensure that we keep all the changes are under control. They have to be approved, and they have to be assessed, and if they impact the security control board enters into the scenes and they approve the changes, and in case we proceed with implementation. Otherwise, if we see that it affects the security level of the Copernicus, in this case, we need to define the necessary countermeasure to put in place in order to prevent that we create a security flows from the change. I hope I responded to your question.
I haven't heard two themes which are in the press all the time concerning security. It's bring your own device and cloud services. Is it no problem for you, or?
Here we are in a slightly different environment because here we talk about data centers. So the bring your own device concept did not apply. We do not allow to bring your own device inside data centers. It's not possible. We are thinking about procedures to keep this under control because mission managers want to have the mission control on their tablets. But this is something we are facing with, but it's not a big issue because it's not the main objective. It's not something that is happening right now. For the cloud, Francesco is mentioned that we have set up a sort of a pick-up point infrastructure, which is a sort of cloud where we deliver the data that are to be provided to the end users. There are other infrastructures that are coming in order to provide cloud-based services, but we are still working on this.
What I meant with cloud is that users bring their data out of your infrastructure to share it with external colleagues and so on. This problem we face very.
Yeah, the main point is that we need to grant the integrity of the data that we are delivering to the satellite from the satellites, and then we need to ensure that the service deliver a product that is really based on this information. Beyond this, we don't have any further constraints. Confidentiality is not really a constraint. There's not a real issue in sharing this information with other people. Of course, if integrity is impacted, there may be a problem, but we can arrive up to the border of our infrastructure with that.
Thank you. I actually have a question that maybe some of us that are not from Europe, could you, I'm amazed at the scale of this, and you mentioned right now that there's just one satellite. How many are expected? And I can only imagine that then this just, for each satellite, the scale then just gets exponentially bigger. Can you or Francesco comment on that?
Well, the architecture of the network and also the security has been designed with the scalability in mind. The infrastructure that has been set up to now is already ready to host the 3 missions, because one is already in operations and then the other 2 coming. Sentinel-2 is going to be launched next June on the 22, and then there is Sentinel-3 is going to be launched in November. But the ground segments are already integrated into this infrastructure. So all the numbers that you see is because we already have these satellites in place. But all the sizing and all the design from the network in particular standpoint, probably Francesco wants to say more, has been done with the target in our mind. So we know we're going to host 5 different satellites. They are 10 basically because each satellite is a system of satellites, so 2 satellites are together, and more missions will be coming in the future. So this has been addressed, hopefully in the right manner. Of course, what we have seen that there is really a huge amount of data that is being circulated and distributed, and much more is coming. So probably at one point in time we will need to find a new killing technology to deal with this circulation. Something?
Okay, thank you very much.
Thank you.
So, here's my number. Wonderful. So we seg now to a different area here. We have Mr. Richard Hughes Jones, who's the Senior Network Advisor in the Office of the CTO in the Gironde Association. And Richard is going to talk now. We're segueing to the SKA and a fascinating presentation on networking, but he's going to cover a lot more than just the networking of this large-scale effort. Richard?
Oh, thank you, Anna, for the introduction, and thank you also for the opportunity to tell you a little bit about what's going on in the SKA and how we're doing the networking there. If I can figure out how to use the control, which I can't, which is a good start. Is there a button on here? They don't appear to work.
I think if you just do this. There we go.
Okay.
So just press that.
Thank you very much. So the SKA is made up of a set of elements. As you see on the screen here, there's the low-frequency antenna, the dishes, which you're very familiar with. Feeding from the dishes and from the antenna, you have to go through some smart electronics to pick out the signal from the background and then transfer that to supercomputer. All this is within the telescope instrument, and the supercomputer, or the science data processor as it's known, produces the sky maps and other data products and stores them in archives. You need some glue, the network, to join this all together, and of course you need infrastructure. You need power, you need fibers, you need roads to connect it all together and to make it realized. You've got to be able to control the system, so this is the role of the telescope manager, and we've also got to have a rollout plan so that we can actually construct this over several years. What's been happening over the last 2 years is to start doing the planning of the various activities of these elements. And they completed their preliminary design plan at the end of last year, and there was an external review for most of the elements to evaluate what they produced, including the cost of what it would take to build it. This was fed into a rebaselining exercise. that the office, SKA office, who is the ultimate design responsibility, carried out, and this was approved, their suggestion was approved by the board earlier this year. And what this now means is that there are now 2 telescopes, not 3, and also the number of elements has been reduced. So we have in South Africa, SKA mid, looking at the frequency band. Sorry about this. I one day will find out how to drive it. Here, which is quite a nice big range, it's made up of the precursor. Meerkat is a precursor to the SKA, and the 64 dishes, 133, it's about 200 dishes there. The low-frequency aperture array is constructed in the outback in Australia and consists of a very large number of log array antenna, and they're grouped into stations. Here, again, the total number has been reduced. That also, I want to remind you how it's constructed. The idea is that you have a core to get most of the antennas, but you have spiral arms. And here's a more detailed one for South Africa, where it shows that although the antenna may be fairly smoothly spaced on the spiral arms, the way that the cables have to go and the fibers are somewhat longer. Typically, the radius is about 1 to 3 kilometers for the core, and about 100 kilometers for the spiral arm. So that gives you a scale of SKA1. ARNet, GÉANT, and SANREN are the academic network partners in the signal and data transport element, which is responsible for the networking of SKA. SKA requires 3 basic networks: the data network, the synchronization and timing network, and the non-science data network. So what we have is that the data flows in one direction, here from the antenna to the correlator, from the correlator output to the supercomputer. It is a continuous flow of data at the rates that you'll see on the next slide. In order to operate SKA, you have got to have a coherent time system. So we have a clock and a maser ensemble so that we distribute phase across the entire system. And we also need to control it, as I said earlier, which is the non-science data network here. This is the new estimate of the rates required. They are fairly modest, but compared with what we had before and what you may have seen in previous presentations. Just to give you an example, in Australia, looking at the rate between the signal processor and the science processor, that was close to 97 terabits. That would have been an interesting challenge. We could do it at today's equipment, but we'd probably need something the size of this room. With these more modest rates here and here, we've actually done that already on the GÉANT backbone, and I know ARNet are testing suitable equipment from vendors at the moment. So we believe the risk is quite low, and it is certainly very doable indeed, even though the rates are still very high compared with an NREN network. So the digital data backhaul, which is connecting the antenna to the correlator, is essentially a quite simple COTS system. For the mid, we need to pump about 97 gigabits. It is continuous, there is no burstiness, we don't have to worry about TCP, and we'll be using standard 100 gig interfaces. For the SKA low, we will connect those stations with a couple of 10 gigabit links. To move the data between the correlator and the supercomputer, we will do something very, very similar to what the NREN backbones do at the moment. We use an optical transponder system. We offer client-side 100 gigabit Ethernet. We move that on optical transponders to a line side. As you may have heard from Sienna yesterday, they already have 200 or 400 links and deliver it to the science processor at the other end. The non-science data network is like putting together a large campus, but it obviously has to be as resilient as possible. But given the topology I showed you, there is only one fiber bundle that is running out along the spiral arms. There is only one fiber bundle between the supercomputer and the correlator. So we have to do our best to avoid problems with equipment. Let me turn now to what comes out. What is the science? What is the results? And what sort of data rates might we have on the world network? So there's a lot of different types of data products. The most common that people think of is what is known as the data cube. This is a set of sky images as a function of wavelength. They are something like 18 terabits is the current estimate, and there will be several of those a year. Unfortunately, I don't have an estimator of n. So if I put in something that's reasonable and that's being discussed, then maybe we need about 30 gigabits continuous. Another part of science is the Epoch of Reionization, where here you need not the processed output and sky maps, you need the raw input. It's the output of the correlator, which looks something like this in the UV plane. You need that in order you can take it and do the computation outside the telescope. And for that, you need a pretty large supercomputer outside the SKA telescope. And here, well, this is impressive. However, there is some mitigation in that you can't take this data all the time, and so the averages could be quite low. Well, a few tens of gigabits. Equally, for the gravitational tests with the lensing, you need similar large amounts of data. It gets slightly better with pulsars and VLBI. Here we only need maybe 10 gigs for pulsar data, and we can already do 4 gigabits for VLBI, so we're putting in 10 for that at the moment. So what's the bottom line? Well, there's an awful lot of data. People in the supercomputing area are looking to see how to reduce this, how to make it more tractable, but the current thinking is it's most likely we need 100 gigabits out of each telescope. They have a model of how they would do the processing, where it might be done. And this is one of the pictures I've taken. Here are the instruments. These are the supercomputers outside that I was referring to. They've got some ideas which I think are extremely sensible. It is a fundamental requirement that there is a replica, so data has to be moved out. Exactly what that looks like, how it is compacted, is being worked on at the moment. They only want to move the data once. So it might be a ripple effect going across the world to where the scientists really are. And the protocols must work to move that data. As we heard from Copernicus, they have similar challenges as well. Let me have a little look at how the two host countries are connected. This is South Africa, and there are two routes. The CCOM cable, the CCOM cable running this way, but it's most likely they will use WAX, which is running between London and Cape Town the other way. There is enough capacity on there. At the moment, it is running two 10 gigabit links for the academic South African world. But in the future, i.e. next year, the operators will move each wavelength to 100 gig. The government has agreed that they can do that. And once they light that wavelength, then the SKA or the scientists will have to find funding for the OPEX. Much the same in Australia. The main routes here run out towards America from the east. There are other links, and there's discussions here about possible new cable systems, but they've been going on for some time. Currently, these links are running at 2 times 40 gig. They will move to 2 times 100 gig. Again, there's going to be a requirement to be able to fund the science traffic. So we worked together to try and put to some idea of what is this going to cost and where is the data going. I must emphasize, this is Richard's guess. It is Richard's guess in that I do not know where the regional centres will be. The SKA board has not approved this yet, to my knowledge. But it is reasonable that the regional centres will be located somewhere in the areas where the SKA partners are. So that's where we've got put them as they are. And the paths here indicate the most likely paths that the data will or could move, and here is a cost. This cost has been generated for 100 gig in 2020, and it's based on what we have actually paid at the moment for either 100 gig where that's available or 10 gig where that is available, projected forward by something that most people think is reasonable. This is a large amount of money. Some cost model will be required. Obviously, the NRENs involved are working with the scientists, just like the Copernicus people were saying, to try and work out the best way to do this and how to take it forward. So, in summary, I hope I've outlined a little bit the work of the SKA and the various consortia. As I said, ARNet, Géant, SANREN are very heavily involved, not only in the NREN domain, which is outside connecting the telescopes to the world, but also within the telescopes themselves, advising and helping and even leading the design of the various network components. I think I've shown you that without networking, you actually can't run the telescope. It won't work. And we're well aware it's one of the risks that should a digger go through one of the main fibers, then observing will stop. Everybody accepts that, but that just shows the criticality of the networking in this device. I've also tried to illustrate that it is a worldwide community and data will have to be moved around the world in order for the scientists to be able to access the archives, move the data to where they can do the computing, which will be considerable outside to get the physics out, do the comparisons, produce the papers. And also for VLBI, there's a need for real-time feeds. And with that, I'll leave you with some nice pictures.
Firstly, thank you very much. It's this kind of presentation which makes TNC so valuable. It's really interesting. A lot of what you said was predicated on smooth movement of data. So what happens if there isn't that smooth movement of data? Is the data lost? Is it cached? Have you got a backup? And this isn't going through the pipe. This is just a normal disruption. So
the data is generated by a clocked sampling. So the source of the data at all the telescopes is a regular clock. So the data comes out at a constant rate, as I was emphasizing. When it gets, and that is between the telescope and the correlator. In the correlator, you look at each baseline and each frequency band, and you integrate for a certain time. They call it the dump time. At the end of that time, which it can be dependent on the length of the baseline you're looking at, i.e. the distance between the two telescopes, you have a small amount of data to put out. However, everyone is doing that at the same time. So if you like, The numbers I've quoted you are an average over the dump period, but you are getting an enormous burst out at that point. There's two ways to solve this problem. One, the correlator people actually don't dump it at the same time, but they dump it in a staggered fashion. They do dump it all at the same time, but they can't generate the packets simultaneously in their FPGA hardware, so it automatically puts them out at line speed. And we transport it as 100 gig point to point. There is nothing in the way, there's no contention. So we believe that with those mechanisms, we don't have a problem. Does that answer the question?
Hi, Richard. My name's Leon Staphorst. I head up Sunren. We haven't met in person. Maybe some comments and slight corrections here and there regarding the capacity out of South Africa. Most definitely, the West Africa cable system will be the cable that we'll use. The Department of Science and Technology in South Africa invested about $60 million in a 7.4% right of use for 15 years, a 15-year IRU. So the system will go through various upgrades, the WAC system. By end 2016, we'll actually have not 200 gig wavelengths available because the upgrade is a partial upgrade to 100 gigs. Some of the wavelengths will remain on 10, which means the South African NREN, Sunren, will have available 178 gigabits per second that it can activate as it sees fit. By 2020, the system should have gone through all of its upgrades, and we're expecting that it's going to end at about 400 gigabits per second per wavelength. And the last thing is around the Oem cost. You're quite right. Obviously, the SKA will have to fund Oem costs to take data out of South Africa and Australia, and institutions that want to come and fetch data will also have to obviously pay for that connectivity. The cost we expect to be, in terms of the current input drivers for wax costs, is about $1 million per wavelength per year. Mm-hmm. That probably will scale a little bit up as the wavelengths go from 10 to 100 to 400, but that's about the ballpark.
Thank you very much for that clarification. I did know some of the detail, but did not think I had the authority to make all that information public, and I was trying to give an outline. But thank you again for that. I agree with you. I had a range of prices for the link going from half to something like, was it 3 million per year? So we are in agreement, I believe.
Yes, it could very well end up at $2 million a year per wavelength, and the SKA will most probably use 1 to 2 when it's finalized, out of South Africa. Yes. At least 1 to 2 wavelengths, yes.
Good day, I'm Roderick Moy, also from Sunren. I noticed in the ESA presentations that security was a fundamental concern, and that a lot of the network design also seemed to be based around that, and we had that as a very serious consideration. But I didn't see any security in your network diagrams. So can you please elaborate on to what extent security has been considered and perhaps how it will be implemented? Because I saw things like, for example, that the internet and the control of the telescopes runs on the same network. So obviously, you know, how to secure that is very important. Okay, so I did have the word security, but you're right, it was only in one place. The non-science data network is made up of a set of services running over an infrastructure. And the picture I showed you was the infrastructure because it was easier to explain. Security is, as you point out, and as colleagues beforehand pointed out, extremely important. However, we have to do a risk analysis, and that has been done, the initial one at least, and working out what is the worst thing that could happen. And jokingly, one of my SKA colleagues said, well, probably the worst thing that could happen is that the telescopes do a football crowd wave. Seriously though,
The services are isolated, very much like you mentioned about the various layers of security, zones of security. So you will not have direct access to the network that does the control. You will be able to have controlled access to the various components, but it will go through several layers of AAA, so that you can actually be sure that only the right people are allowed to connect. We have had discussions with places like CERN, because it's quite similar. In general, there is no life-threatening actions in the telescopes. It's not like a medical facility or a rescue facility that you need to be very careful. So we balance all these things. The non-science data network design allows us to put in choke points, break points, such as firewalls and other detection devices, just as you mentioned. And also, the data moving will be in a DMZ outside, because if we want to transmit 100 gig, you are not going to put that through a firewall. Current firewalls, let me put it the other way around, be more positive. Current firewalls won't support that. So yes, we take it seriously. There will be a detailed policy document for SKA. SADT is contributing to that. And as I say, we have arranged meetings with other science facilities to get their input.
Okay, we're also interested in participating in that, so I'll have a chat with you afterwards. Thanks.
Okay, thank you. Thank you.
Thank you, Richard. Our next and final speaker is going to now, as I mentioned at the beginning, now talk about a specific country, and in this case, Chile. And Sandra is going to cover a little bit more the amazing challenges as that being the driver in support of the facilities there. Sandra Hake is the REUNAS, the Chilean National Research and Education Network. She's been the CTO for quite a period of time, also very much involved, more than 15 years there, working as a network engineer and as the CTO for a number of years now. So Sandra, welcome.
Thank you, Anna. Good morning to everyone. It is a pleasure to be here and be able to talk about Chile and our challenges during this time. What is that? Yes. So let's start. Please forgive me for my English. It's not the worst I would like to. I'm not sure if you know that we are very, in some way, lucky country, because we will concentrate in the order of 70% of the global telescope facilities of the world in the following years. So, of course, it's a great challenge, but also a great opportunity not only for the NREN, for the country, in many fields. On that way, we have been working to have the majority of the institutions related with astronomy, not only the telescope, but also universities today being part of REUNA, and of course we are working to have everyone connected to this network. And how we have been able to manage to have this institution, here is a list, I'm not going to read it, just to remark that in the last 5 or 7 years, we have been working with the observatories to build together the network infrastructure. So I'm going to emphasize on that. But of course, this technology challenge are not only of infrastructure. I wanted to put this just to emphasize that Chile is a difficult country in terms of geographical situation, because it is a long country And it's a very, very thin country. So that's why I'm saying that, because it's not easy to find telecommunication solutions along all the country. Actually, we have the main road, of course, for the north up to here. And this part of the country that I'm going to talk at the end is not covered by the main road. It sometimes has to pass by fjords or by the sea. So that's why I'm saying this. And also it's important to keep in mind that the main population of the country is concentrated in the central area. So that means also the telecommunication infrastructure tend to concentrate on that place. Well, as I said, we are facing challenges. There is a new telescope being constructed, the LSST. Probably you have heard about that. It is a survey telescope that will do a survey of the sky by 3 days. And it is amazing, the infrastructure. Of course, we heard before another amazing infrastructure. It's called my attention, the camera they are using. But in terms of networking, there is expected this telescope will produce in the order of 15 terabytes of data per night. That is a huge challenge. So in terms of connectivity, the telescope is expecting to need in the order of 40 gigabits by the following 2 years, and when it's in production, 100 gigabits per second. We are the institution taking care of construct the network. The telescope is needed from the summit of the telescope to this city, La Serena, and from La Serena to Santiago, where is the link to the international institutions belonging to this telescope. In terms of networks, here there is a brief detail, but I wanted to explain more deeply the message that for us as REUNA, this is of course is to commit the requirements the telescope needs, but we are working in synergy. So the infrastructure is not only built for the telescope, it's built for the Chilean network, so we are going to share, of course, the infrastructure, the network. And some technical issues, we are going to have a long-haul fiber connectivity. It is already decided. It is a new project of some telecoms company, but we are going to have direct access to a pair of fiber from La Serena, the city where is the telescope, to Santiago, which is, in this case, 1,700 kilometers of length. And to connect the observatory to the near city, which is La Serena, also, we are going to have 2 pairs of fiber, and inside the land of the observatory will be a fiber construction with more pairs, because obviously that we have to do it on that way. And we are going to light the fiber. We are working in parallel in this time to find the best solution in terms of equipment to light the fiber with lambdas of 100 gigabit per second. How this will be a fiber that doesn't have redundancy because the budget, we can't buy a pair of fiber by another road. Actually, there isn't. We are going to implement also a redundancy backup link by a telco through a lambda. So this is the LSST. We are working on that project, and it's probably the infrastructure we are going to work in the following 2 years. But in the past, and how we have been confident that we are going to do it successfully, is because we have working with astronomy, as I said, in 2 projects. EVALSO, probably one of you have heard about that. It was a project developed by 2008-2011, co-funded by the 7th Frame Program of the European Commission. And this is a very, very relevant project because we achieved 2 milestones, new milestone for us. It was the first construction of fiber in the middle of the desert. Was an amazing achievement. And here I have some picture of the machine doing the dig. and then was put the fiber in the earth. So it is a fiber from the telescope to the near city, which name is Antofagasta, and from Antofagasta to Santiago. In Antofagasta we have already, we did it, our point of presence, and also in Santiago. There are two cities in the middle. We could achieve as an aeromodality a wavelength, and in this moment it is lighted at 10 gig. A wavelength is in a long term, 10 years. Although we have been passing 5 years since the project started, so 10 years sounds a long time, but it's not. It's completely in operation, this project. The other one, ALMA, it is similar to Richard told. It is an international partnership telescope, involved 20 countries, 66 antenna, etc. There is a lot of information, of course, in the ALMA websites. But in terms of connectivity, we was extending the physical construction of the network because this was the second construction of fiber in the desert with a different technology. You can see a different machine here, which make the dig and put the fiber immediately at the same time. It was 120 kilometers of fiber from the telescope to the near city again, called Calama. Here we have an extra challenge because this telescope is located at 5,000 meters of altitude. So we was concerned about the equipment behavior. But we have the equipment working since several months, so we haven't had problem. So Dwdm equipments, at least in this scenario, are working well. And from Calama, which is here, this is the fiber. From Calama to Antofagasta, I already mentioned we have a POP here. We extended a Dwdm Lambda because we're learning how to do it, negotiating with the telecommunication companies. And from Antofagasta, I continue to Santiago. Another relevant thing here is this project not only construct the fiber and extend the Lambda, but we could able to have access to a backup link, but now by Argentina. Why I'm mentioning this? This will be in operation in the future, it's not ready. This infrastructure is ready and we are in a testing period. I mentioned the backup by Argentina because, as I said, Chile is a thin country. So we don't have too many roads or alternative roads. That means also we don't have alternative fiber. So it's relevant to have this because we plan, of course, to make a ring between the north and to Santiago by Argentina. Actually, you know that we have earthquake, so we need to have backup scenario. Well, that was astronomy, and I wanted to mention this because it's related, and the session was big data. It is related with APC. This is a national project. It's relevant because many things, among of them, allow us to build now a metropolitan Dwdm network. So give us another opportunities. But I wanted to mention that last year, as a Chilean scientist, making or using all the pieces together, being able to discover a supernova. I know the title, I don't know the details, of course. But relevant here is they use the aura data on the telescope that where the LSST will be located, the HPC cluster that is located in Santiago, and the network to transport the data. And they did the discovery together. So it is a very relevant case of use, how the infrastructure can be used together. And well, just to mention, of course, I said Reuna is connected globally, and in this case, there is happening a new project called Vela, and I wanted to mention this because it is a new fiber from Latin America to Europe, and that means the academia will have access to the capacity of that fiber, and that is related because we now are forced to build a fiber terrestrial network in our countries. So that is important in the case of all the countries, but in the case of Chile, because the north is the path to Peru in this case. So in terms of the strategic vision we are using to construct the network, we are not only considering to work in synergy with the astronomy, of course, with this project to continue building the network. And I have to move up because I know that I don't have time. But of course, I cannot talk only about the north. I'm going to skip and then back again. The network is along all the country, so excuse me, but I have to talk also about the south. I'm from the south, so I can skip this. And of course, in the south, there is also, in the south, there is also research. And in that way, as I said, here is not a road, so it's a very difficult geographic place. Actually, the current connectivity is by satellite or by Argentina, so it's strange. So I just wanted to mark that the government decided to build a project and to ask tender for build a fiber from Puerto Montt, which is the city, to Punta Arenas. So we are very excited about this project because, of course, we wanted to use the infrastructure, and it's the aspect we have been talking with the government. So I'm just finishing with this. The idea was to show that how we in Synergy have been constructing the network and how all the pieces we are trying to join together in a coherent strategy to build the connectivity. By the way, REUNA is a private consortium not funded by the government, so we have to be able to work with the different projects. And this is just to summarize. Of course, as all the entrance started with universities, and in this case, in the latest 80s, and we have been able during the years to include the observatories, research centers, and increase the network in collaboration with the institution. And of course, we see the future reaching all the institutions in the country and increasing the connectivity together with the astronomy and other science fields we can work with. So that is, thank you.
Thank you. We have some time for questions.
Can you hand over this question because I have problem with my ear.
Any questions?
So my question relates to the fact that observatories are often built in very, very distant places on the top of mountains. Places where there isn't a very strong business case necessarily for telecommunications providers, maybe to build infrastructure. Do you find that's the case in Chile? And do you work on projects to maybe connect local communities in these distant areas when you connect an observatory in a very remote place?
Yes, no problem. Que si le puedes explicar un poquito cómo es el return on investment, que no puede ser mucho porque no hay el caso para los negocios, y cómo están manejando esto, pero si está beneficiando otras comunidades también. I did my best job in attempting to translate the question.
Thank you.
But let us know if we don't get to it.
Thank you. Yes, well, in this case, this kind of projects, as I said, the first was co-funded by the European Commission. The LSST is funded by NSF. And the idea here is to use a business model in case of acquired infrastructure as an investment and pay at less as possible in terms of maintenance. So in that way, it is an economy for everyone. It is good for the company that can give the infrastructure, and it's good for the institution because, of course, has economy in terms of the money it is paying. I'm not sure if that was the question.
Other questions? Well, I personally have to say that having visited Chile 10 years ago, I'm just outstanding. It's amazing to see what a driver this has been, but also the fantastic collaboration.
Yes.
And I think it illustrates the point about the role that national research and education networks can play in partnering and working with these communities that are doing, the science. And let's see where we are in a few years. I can't wait to invite, and let's get this panel back together in a few years. Because as these things start rolling online, I think it's going to be really interesting to track how the instrumental role that we're playing. It gives me faith in all the work that we're doing. Job security, if anything. So thank you very, very much. And please join me in saying thank you to this wonderful set of speakers. So we are adjourned, and please go have lunch.